Okay, so welcome everybody to our next presentation in our series of workshops dedicated to the machine learning. And we are very happy to welcome today Dr. Avik Roy. Avik is a new postdoctoral research associate in the Center for AI Innovation at NCSA, and his work is concerned on applied to physics. So he's going to present today about physics-inspired neural networks. So Avik, welcome, and please take it from here.
Okay, thank you, Professor. And it is a great privilege to be here to be able to talk about some recent work that I have done right at the moment when I was transitioning from my grad school to this postdoc position. So this talk is based on a very recent paper that we put out in arXiv, and you can see the link and the corresponding GitHub link as well for the code. It is available there, and I think it comes with a nice set of instructions on how to run these codes there as well. So if anyone is interested, just you can fork the repository and get it on HAL, and you can start running it. So I will start with a very simple introduction to what physics-informed neural network, or as we call it, PINNs, what PINNs are and why they are so interesting and useful. So let me start with this. Like, we are familiar that neural networks are very popular these days, and they have been widely used for regression problems as well. And one of the main reasons that neural networks are so popular is because it has been theoretically proven that neural networks provide data as universal function approximators. So what you have in a typical neural network, like a multi-layer perceptron, is you have a set of input features that are followed by hidden layers with nonlinear activation that eventually takes you the desired output. So what does it mean that neural networks are universal function approximators? It means that you can actually train a neural network to mimic arbitrary nonlinear functions with very high accuracy, as long as you have a sufficient number of nodes and hidden layers and embedded within them, and a large enough training data set with an appropriate choice of loss function that allows backpropagation of gradients and eventually correction of these weights and biases to get them to the desired point. So in this way, you can think that a neural network eventually can become a very reliable surrogate for a nonlinear function. If you know what your outputs are for a large number of sample points, you probably can train a neural network to reliably approximate the function that these inputs and outputs are actually trying to get. This takes us to physics-informed neural networks. Now, how this feature of neural network can be useful us to learn physics or to apply them in inspired situations. So as we have already seen in our early physics textbooks and early physics research, that in many cases we are actually concerned with a spatiotemporal evolution of physical fields, like the case of electromagnetic waves and the Maxwell's equations that actually describe them. And these fields and evolution of them are often described by partial differential equations. So the question is, can we actually, so in a way, this is also an input-output relationship, and in a way, it's also a regression problem. You have as your input as the coordinates of your space-time, and as output is the functional values of the fields that you are interested in. So the question is, can you actually try and let a neural network, which will somewhat have a structure like the one that you are seeing in the figure here. You have a set of inputs. This could be the space-time coordinates, and also a set of outputs. You don't have to a single PD or a single field. You can have multiple PDs describing multiple fields in a coupled fashion, and you have some hidden layers in between that are parameterized by some generic set of parameters theta. And the question is, how do you explain, or how you can actually train a neural network to train or learn a process like that? How do you get a neural network to learn how these fields will look like at different points in space and time? Now, we can actually think that, or we can have actually seen in literature already, that PINNs can solve a set of coupled PDEs like the one I was talking before, as long as we know the PDEs are uniquely solvable, which is actually based on the mathematical knowledge, the huge set of mathematical knowledge we have based on the development and solving of PDEs. There are many ways to actually understand whether PDEs are uniquely solvable without actually solving them. So there are ways, in many cases, we know that certain PDEs are uniquely solvable. And also you have to know the spatiotemporal boundary conditions so that you can actually embed them in the process of learning the solution of these. And the parameters are optimized in a way so that you can actually train the network to obey the physics, the differential equation that actually describes the physics of the spatiotemporal evolution that we're interested in. And this is where it becomes interesting. I mean, if you have a very large data set that describes the field that we're interested in solving for a large number of space-time grid points, you can probably simply train the network to find its functional form right away without caring about what differential equation is actually there to describe it. However, if you have only a small set of data, that because the data is probably expensive, or it is probably hard to get, or it's simply not probably permissible data at a very large number of points, then physics-informed neural networks come in handy. So we are basically trying to evaluate the behavior of a field at a very large number of space-time points, while we only have a small data set to train it with. And that becomes a challenge, and that is where we can actually put in the physics as a part of its learning process. And to do that, we exploit the autograd functionality from modern machine learning libraries. So nowadays, all machine learning libraries, that PyTorch or TensorFlow, has very nice and parallelized calculation of gradients, and backpropagation of them is a very useful tool. So with this kind of advanced tools at hand, we can actually try to calculate the actual behavior of the neural networks in terms of its derivatives and gradients, and that might come in handy, as I'm going to show in the later slides. So this is the formulation of the problem that we're interested in. So you have the physics, which is just a partial differential equation. The field that we're interested, the set of fields that we're interested in learning, is given by u, and x is the spatiotemporal set of coordinates that we're interested in. And also it might come with some analytically known source functions. It might be, so if you are trying to get the response of a particular to a particular kind of input, you might just know what the input is. So the f of x could be there, it doesn't have to be there. And then we also have a set of initial or boundary conditions. So just for the sake of nomenclature, I might interchangeably use them, because all the initial condition is typically taken on the boundary of time at time t goes to 0. You can also think of an initial condition. So this del D here represents the domain boundary, where we will be taking some sample of points, and we have to know what the value of the fields are, or probably their derivatives, if we're interested in those kind of boundary conditions. And the neural network will actually become a surrogate for this set of fields that we're interested in learning about. And these neural networks will be parameterized by a set of parameters theta, and the training data set can be divided in 3 different parts: UB, UC, and UD, which I'll be explaining in the next slide. So as I told you before, this is where we are trying to learn a very complicated and nonlinear function by training it with a small number of small data set. So what do we mean by small data set? We will actually have the evaluation of the field at a very small number of points, and mostly on its boundaries. So the first data set that we need is a collection of measurement points that we take on the domain boundary, and the physical measurements are known at this point. So the first data set UB represents a sample of points, and a total of NB points, where we know what the field looks like at initial time slice t equals to 0 or the domain boundary of the space domain. And the second set of points is called collocation points. Now, this is where it gets tricky. Typically, these collocation points are where we do not know the behavior of the field, but we are simply taking it as a large number of samples by sampling the domain that on which we are interested in solving the PDE. So we'll take a very large number of points within that domain, but we don't need to know the evaluation of the field in these points here. We just need to know that source function, the value of the source function at this point, if there is one, and I can very easily it because the source function is assumed to be known analytically. So this very point that we are actually trying to use to learn the physics of the problem is called collocation points, where we will actually go ahead and evaluate the derivatives of the network, the gradients of them, and eventually enforce the physics to get it working. And thirdly, we might have some additional data points at some intermediate points that are not necessarily not on the domain boundary, but this is not exactly essential for training it. It is something that would be nice to have. If we have some additional measurements, why not use them? So based on these three types of data sets that we have, we can define the loss function that we try to optimize or minimize. So the loss function will be a weighted sum of the three different kinds of loss functions here. So you know these alpha parameters that you can see, these are the hyperparameters of the corresponding model, and all the results that I'll be showing today are based on the choice of alpha equals to 1. So you do not go into tuning of the hyperparameters in this current work. However, it is something that will be very interesting to explore, and I would be very happy if someone goes and tries that. However, so the loss function will be eventually a sum of three different MSE losses. The first one is coming from the boundary the boundary loss. It is basically trying to enforce that this set of boundary conditions that we have enforced, given by cursive B here. We evaluate those boundary conditions for the fields evaluated on the boundary points and set them to 0. So the first one is the MSE loss for the boundary condition that might include the initial condition at the initial time slice, boundary condition, the spatial boundary. And then you have the physics loss, where we actually take the large set of collocation points and we evaluate the surrogate function from the neural network. Now, once we so evaluating the value of or evaluating values for a neural network is not an expensive job to do. So this calculation does not take a very long time, but it is the when we actually embed this loss function in the loss function we are trying to minimize, it creates that back propagation of gradients that eventually tries to enforce this. So what we are trying to do, we are trying to use and probably the other derivatives of the fields that we're interested in to enforce the PDE to be obeyed by the neural network. And the third loss is from the some additional data. We also want to make sure that we get the right kind of evaluation at those points. So we are trying to impose a MSE loss there as well. So we are trying to use will be optimized by minimizing the loss function. So the parameters will be given by the choice that will minimize this loss function, and you can use standard optimization algorithms, or for example stochastic gradient descent or ADAM, to actually calculate this backpropagation and eventually converge to a point where you have the right set of parameters that gives you a very reliable solution to the PDE. Okay, so far we have been talking, or I have been talking about a very abstract set of problems. So now let's take an example. We are talking about a nonlinear Schrodinger equation. So if you are from physics or engineering, you probably already know what a linear Schrodinger equation is. It actually, the linear Schrodinger equation is a complex field that gives you the evolution of a quantum wave function. But nonlinear Schrodinger equation is much more interesting physical. For example, this nonlinear field that we're interested in, it obeys this nonlinear equation that is given here. It's a complex PDE, so you can actually interpret it as a set of coupled PDEs that evaluates these two fields simultaneously, this U and the V, the real and the imaginary part of the field. And in this particular case, we're interested in a finite spatial domain and a time domain. So we want this to be between the X coordinate should be between -5 and +5, and the time coordinate should be between 0 and pi/2 for the sake of this problem here. And this HXT may represent traveling electromagnetic field in optical fibers or planar waveguides. So this is very widely used in very practical applications there as well. Okay, so the boundary conditions that we're interested in, the first one is an initial condition. So we have a finite set of points on the initial time slice, which are actually taken from this known function. So this is known to us, but not the neural network. The neural network only sees a value, and these values can be corrupted with an error value epsilon I there you can see. And that is where we will be getting more interesting things to learn about PINNs. So at this point, you have a finite set of X points and a finite set of and a corresponding measurements and set of measurements associated with them that might be corrupted with error or might not be. And we also have periodic boundary conditions for this particular problem. We want the fields and its derivatives to be continuous across the to be periodic in space domain. And as I said before, epsilon I, if we enable them, we assume that they are drawn for zero mean Gaussian distributions with a finite standard deviation. Okay, so take a look at how the PINN, the physics-informed neural network, works when you have the perfect scenario. There is no data, no error with the training data. What we did, we took a simple MLP with 6 hidden layers and 70 nodes per layer, and the initial condition was enforced on 50 points on the initial time slice, and 50 more were taken to enforce the periodic boundary conditions. And we took 20,000 randomly chosen points within the space-time grid to enforce the physics. So those 20,000 are the collocation points within the space-time domain that we are interested to solve this problem for. And we iterated this for 50,000 times with an Adam optimizer with a learning rate of 10 to the power -3. And this is what you see. You are seeing here the analytical solution compared with the PINN evaluated solution for the magnitude of the complex field here, and you can see we see almost perfect agreement between the analytical solution and the PINN evaluated solution, and that's nice. So the PINN does a job for us. So this is where it gets interesting. What if we actually take some corrupted data on the initial time slice? Does a physics-informed neural network have a capability of auto-correcting itself? So if you have some erroneous data based on the physics that we are trying to impose on the network, can it learn the analytical form, and can it actually make sure that it retrieves the analytical solution without distorting or without propagating the errors? And by looking at these figures, you can probably think, well, it's most certainly cannot. So what happens if what we did, we introduced a very small amount of error. We took each of these epsilon i's from a zero mean Gaussian distribution with a standard deviation of 0.1. And what you can see in the very first plot here is how the field looks like on the initial time slice. And you can see the training points are not exactly on the analytical solution, but they're slightly corrupted. And you can, if you follow the green curve there, you can see that the PINN evaluated function tries to overfit at certain locations, and eventually this overfitting gets carried over in the later time slices, and you can see a distortion of the line shape of the field as you go ahead in time. So, and this is for a very small amount of error. So most certainly, if you have larger errors with your evaluation of the initial data, the errors that you will be seeing on later time slices are going to be very high as well. And this is pretty interesting, and we try to understand why this actually happens. So we most certainly saw that the PINNs do not have the ability to self-correct as it is corrupted, right? And why this happens, if you really think about it, it has this nice analogy. So once you have the perfect scenario, no errors and everything, your loss function will actually have a very nice smooth structure that eventually converges to a global, that will give you a global minima, and you can converge there. But once you corrupt it with the training data sets being associated with some errors in them, you are actually creating bumps, and you are digging trenches at some places, and you are creating bumpy roads in the smooth surface of the loss function as a function of the parameters, the neural parameters you are trying to optimize. And the PIN will eventually converge to one of those local minima that you have created on the way. So the number of parameters for a PIN architecture is much larger than the number of training points. And this is a classic case where overfitting is there. If you are trying to fit 10 points with, for example, a 9 or 10 degree polynomial, you will get extreme amount of overfitting. And this is the same kind of situation that is happening over here. And what happens once the neural network overfits on the initial time slice and tries to enforce the physics on the collocation points, it eventually ends up propagating those errors dynamically over the entire domain, and hence you see what the kind of deformation of the field structure that you saw in the previous slide. Okay, now the question is, what can we do about it? So one of the classic ideas that we can get from our experience in machine learning is whenever we have some kind of overfitting going on, we try to regularize it. And regularization means typically looks like adding some kind of additional what should I say? Adding some kind of additional loss function to what you have for the usual loss function that will eventually create some additional propagation of gradients and eventually constrain the parameters to be somewhere where we want it to behave normally. So in a way of error correction or subsidizing the effect of outliers, etc. So the question is here is, can we do some regularization for pins? And this is something that is based on a very some variant of pins that is already in the literature. This is called conservative pins, or so-called C-pins. In C-pins, what they typically do, they divide the domain into smaller subdomains and train a pin for each subdomain, and then apply some functional and flux continuity on subdomain interfaces. This is the diagram here actually shows you what it looks like in terms of C-pin structure. You can see, let's for the for what it is worth, you have the x and time, x and t in the two dimensions here, and you are creating an artificial subdomain boundary at some value of x. So your initial and boundary point going to be there. You have collocation points for each subspace of the subdomains, and you choose a fine grid of points on the interface between these two subdomains where you try to enforce the continuity of the function at the continuity of the gradients. Originally, this is meant to be a parallelization technique for training pins, because when you go to high dimension problems, you actually end up with a very large number of collocation points that might be very difficult to train over, but you can create smaller subsets of the problem, and you can parallelize using and train them, and simply enforce the continuity of the function and the flux and subdomain interfaces to make sure the solution looks smooth all over the place. So if you try to construct the loss function for that, it will look like something like this. So the C-pin loss function will have all the independent loss functions for the different pins that you have over the subdomains, and an additional loss function that will enforce the flux and functional continuity at the subdomain interfaces. And if you take a look at this, it certainly reminds you, well, this is a regularizer if you think about it. And that is exactly what we are trying to interpret this interface loss as. So the interface loss looks like this. The messy part is you have functional continuity. So you evaluate the function from the left subdomain and the right subdomain, and you also get their gradients along an orthogonal direction for the subdomain interface. And you also want to ensure that the gradient that you evaluate from the left subdomain matches the one from the right subdomain, and you employ those kind of continuity conditions in your loss function as a part of the interface loss. The question is, we are interpreting this interface loss as a regularizer, and it's a very well motivated one, because if you really think about it well, you can deep in your mind naively think, well, the two different subdomains will try to overfit differently, and these errors are independently measured. So probably requiring the continuity of the intermediate points or the subdomain boundaries probably can control the way it tries to overfit on the subdomain boundaries, and probably that is how it can change the pin's behavior. However, C-pins have their own issues. One of the things is their performance totally depend on where you choose the subdomain boundaries to be. For example, in this particular problem, we are looking at two different choices of subdomain boundaries here. Is where we have two subdomains, and the subdomain boundary is taken at x equals to 0. And the second set of rows, you can see we are taking 3 domain C-pin, where you have taken 3 subdomains, and you have equally distributed the entire x range over the 3 to create 3 equal subdomains and apply the C-pin loss function to optimize them. And you can see these 2 domain C-pin, and all these results are for epsilon equals to 0. So we are associating no errors at this point. Right? Whether a C-pin actually can recover the original function independent of the choice of where you put the boundary and everything, and it actually can. The two domain C-pin actually fails to recreate what the actual analytical function looks like, where the 3 domain C-pin actually can. And you can guess that choosing the subdomain boundary at x equals to 0, which happens to be a very special point nonetheless, because you can see that the HXT form has a local extrema at that point at all over for all times. Probably what is messing up with it, and why that happens is, again, you can take a look at it here. The first set of plots are actually pretty much revealing about what we are trying to tell about the C-pin architecture. So once you add that loss function, the regularizer in this pin loss function to get the loss function for the C-pins, it creates some local minima. Actually allows the function and the gradients that are evaluated at the interface to convert. So you can see the function evaluated by the 2 pins, the left pin and the right pin, actually match with each other almost perfectly at x equals to 0 when subdomain boundary is. And in the second plot, you can see the gradient of the real part of the complex field, which is del u del x, and you can see you have the 2 pins giving you identical gradients, and that's also true for the imaginary part of the complex field, del v del x. But altogether, they're very much different from what the analytical solution is, and that is exactly a classic case where you have some kind of local minima created by this insertion of this additional regularizer in the loss function, and your solution ultimately converges there and gives you this nice 2 pin evaluated solutions. But ultimately, it fails to recover what the actual solution is, what the intended solution is. So this tells us that the C-pin regularizer is not actually is not doing a very good job in recovering what we want, even and it is definitely not invariant with the number of domains or the position of the domains. So it definitely creates some kind of local structure into the loss function manifold, and eventually causes the entire neural network to converge there. And that is exactly why it becomes unreliable, even at cases when you have non-zero error, because using non-zero error only exacerbates the problem of modifying your loss function hyperstructure. And that is exactly what you are seeing. You could the 3-domain CPIN actually has a perfectly nice recovery of the solution, and it matches with the analytical solution when we don't have any error. But as soon as you introduce error, you can see the subdomain solutions do not converge as well anymore, and you have large distortions introduced by these. And in many cases, these distortions are even worse than you would get from a single domain physics informed neural network by itself. And this is because you are actually adding more terms to your loss function that is even further deforming of the loss function in unpredictable ways, and eventually causing these solutions to converge to the local minima. Okay, so that was one kind of regularization that we tried. The second kind of regularization could be coming from something more physics inspired and conservation laws. So in many cases, conservation laws associated with physical processes, we can think of it as regularizers. So we know the Schrodinger's equation has this particular conserved quantity. So if you take the absolute value squared of the field and integrate over the space domain, you get something constant, independent of the of your choice of time. That every time it maintains the total integral of the field strength is a constant. In a way, it is kind of an energy conservation law that is associated with this nonlinear Schrodinger equation. And so what you can try to do is you can try to create slices of time domain and evaluate this quantity on those time slices and apply a loss function that tries to impose this constancy of this particular quantity as a part of the regularizer. And it actually somehow helps. If you take a look at the values that we get for this conserved quantity without regularization and with regularization, and you can see without regularization it's still pretty much flat, because if you look at the y-axis, it is between 0.79 and 0.80. It's not much of a difference, something of the order of a few percent, but it eventually becomes even stronger. Like this constancy becomes even stronger when you actually apply this regularization into your loss function. And you can see the variation of the y-axis in the second case is actually much smaller than the first one. It's almost an order of magnitude smaller. So it basically says that applying this conservation law as a regularizer can actually do you some good, and it actually can try the analytical solution to some extent by constraining how the function can vary at different points in time and space. But it doesn't do a job sufficiently good enough, and you can see what I mean by that in the set of plots that I am showing you here. You can see the evolution of the field as a function of time and space here, and you can see that while regularizer actually helps maintain the conservation law, it does not by itself ensure that the analytical shape is recovered by the PINN, and it simply tries to compensate overshoots at one place by undershoots at a different place, and something like that. So that is exactly what we are seeing here. So that tells us that the different kind of regularizations that are inspired from physics do not do a good enough job to stop the pins to overfit on the initial time slice and eventually propagate them. And so we have to try something else, and that takes us to Gaussian processes. So let me introduce Gaussian processes a little bit. So think of a physical process xt, and at each time instance, the t is a continuous variable. It can be time, and the most common way of interpreting this t index is as time, but it could be any other space index as well. You can think of this physical process xt as a collection of random variables. So if you sample it at any given time instance, you get a random variables. And if you take a finite collection of samples, they will jointly represent a Gaussian distribution, and that is what we mean by a Gaussian processes. And with this definition in hand, you can actually think that, well, the way we introduced our errors, if you remember in the very first slides, we introduced a Gaussian error with the measurements that we had for the initial time slice for the real and the imaginary components of the field. You can think, well, we are actually talking about a Gaussian distribution, a joint Gaussian distribution here. For example, for at any instance of x equals to xi on the domain boundary, the expected value is given by this function here. The expected value of the imaginary component is 0, and the covariance between any two is given by this sigma square delta ij, and together they actually represent a jointly Gaussian distribution that is driven by these mean values and these covariances. So essentially, treating this entire ensemble as a set of Gaussian processes can actually give us interesting insight on how we can actually go about managing these error propagations across later time slices. And what we can do think of instantly is allowing a Gaussian process regression to obtain a joint distribution of any finite subset of processes, finite subset for the process. So so what you can do, you can apply a Gaussian process regression on the initial time slice and eventually allow the result of the regression to be your representation of the field on the initial time slice, and eventually train the network on that fitted Gaussian process to learn the field's behavior at later time slices. And the pairwise covariance for any two instances of u or v can be estimated by a kernel function, and optimizing the Gaussian process is actually optimizing the hyperparameters of the kernel function to get a maximum log likelihood for the fit that we're talking about. So that's exactly what we're trying to do. So Gaussian processes are known to be very good smoothers, and they have this a nice touch that if you can actually choose the kernel well, and you can actually make it outperform other smoothing techniques. So you can actually think of smoothing techniques like a fifth order polynomial or smoothing splines. But compared to these, it has been shown in literature many times that using a Gaussian process to regress over the set of observations can do a much better job and much robust job compared to what you have, what you might have in from polynomials or some other kind of smoothing techniques. And this is something that actually can be very useful to us, since we have seen that neural network does not possess this capability of stopping itself to overfit on the initial time slice. We are taking a nip it in the bud approach. We are trying to say, well, you don't have to know about this irregularity. We will handle it separately, and we'll give you something that you can deal with. So we take an RBF, a radial basis function. This is basically a kernel function that measures the covariance as a function of a Gaussian distribution, and in addition to that choice of point, we have some part of the kernel that takes care of the noisy part within it, and we want to fit it with the data that we have, and we want to make sure that as this particular choice of kernel is a very good one when the surface that you have is sufficiently smooth. And that's what you can see here. The top plot is for u and the bottom plot is for v. So you can see that the errors are all over the places, but the Gaussian process fitted values actually lie on the analytical solution almost identically at every time instance. And for the v here, you can see we are at the actual value of v on the initial time slice was identically 0, but you can see the values of we measured are all over the places because of the errors that were introduced. So we are taking Gaussian process fitted, which actually keeps it pretty close to 0 all over for all values of x. And with this kind of choices at hand, what we can see, we can actually apply this Gaussian process-based smoothing technique for pins, and we can train the network on the smooth version. So in order to do that, we used a cross-validation technique in order to make sure that we are making the right choice for the kernel function. We took a number of different choices for kernels, and we saw which actually allows us to get the best estimate of the values that we observe on the initial time slice without overfitting them. So in order to do that, you might know about something called k-fold value. You hide a certain set of initial observations on the initial time slice, and you do a Gaussian process regression on the rest of them, and you try to see what regression actually gives you the best estimate of the observations that you actually hit from the Gaussian process. And based on that, we found out that this RBF plus white kernel actually did the best job in doing so. And then we apply the Gaussian process regression on the initial time slice data, and eventually what we can do, we can now take the fitted value, the Gaussian process fitted value of these initial time slice field values as the ones that we feed to the neural network and eventually approximate to obtain the solution for the PDE. And you can see at the very last, as you can see at the different time slices, the analytical solution, which is given by this green line here and also called the mean for a reason, we can actually see the analytical solution pretty closely matches with the one that is obtained from the PINN here after doing a Gaussian process on the initial time slice. And this is an encouraging result, and it also gives us something additional, something bonus on top of that. So you can see these gray bands, which is marked as one standard deviation around the mean value that is given by the green line here, and it is one of the many slices I showed you from the previous slide. And this green band deviation. Now, what do I mean by that? So once we were trying to learn the solution of the PDE using an unregularized or unsmoothed version of PINN, what we were getting as a corruption of the estimated line shape. And with this particular approach, we have removed that corruption. We now have a line shape that actually replicates the exact solution pretty smoothly. But since it is a Gaussian process, it also gives you an envelope of variance, right? So it's a Gaussian process. Any two taken over any two space points is actually jointly Gaussian distribution. So you can calculate and those variances can actually be used to find how you can actually, how these errors, these noises, these corruptions that you saw on the initial time slice, how they can actually be used to calculate uncertainties associated with the solution of the physics-informed neural network that we get at later time slices. And that's exactly what we are getting here. And it is done using a simple technique. So if we want to get this done analytically, so we want to propagate these uncertainties analytically. So we have the uncertainties on the initial time slice. We want to get what it look like. It will look time slice. It will become a very difficult problem because you have to invert a Hessian matrix, which will be very large, probably millions of probably a million dimension or so. So instead of doing that, what you do is we actually start with training the neural network for GP smooth initial condition. Then once we have trained and converged, we change the initial conditions by the +1 sigma or -1 sigma band. And then we start with the trained neural network and retrain it with a changed set of initial conditions, and that retraining will actually cause a small deviation of delta theta. But since we already have converged for the mean value, you can think that this retraining will be very fast, and it will not it will probably take 1/10 or 1 hundredth of the time, depending on the complexity and the level of noise you introduced to begin with. It will take a very little time compared to the training of the neural network, and eventually give updated set of weights and biases for the MLP that you are trying to use to estimate these fields. And then using those updated parameters, you can calculate what the line shapes will be and use those line shapes as your envelopes for standard deviation at different time flags. And that's exactly what we're doing here to find the envelopes. And you can see you can get a very reliable estimate and a very nice estimate of deviation here. Okay, so that's the propagation of uncertainty part here. Now we want to dig a little bit further, and we want to talk about something called sparse Gaussian processes. So the thing is, once we were training with a standard physics informed neural network, we needed all the observation points. Those were important to get the things going and training. However, since we are already using a smoothing process using Gaussian processes, the question is now we can take as many, after the fitting with the Gaussian process is done, we can take as many initial time slice points from that fitted Gaussian process as we want. But the question is, do we actually need all the observations to optimize the Gaussian process at initial time slice? Right? And can we actually use a sparse subset of observations to optimize the Gaussian process regression? And the reasoning behind it is something like that. So we are talking about very simple problems here. It's two-dimensional problem, one space and one time. So probably fitting with all the observations you have is not a very, very big deal. However, once you go to a 3+1 dimensional or 4-dimensional problem, for example, you want to use a neural network to solve Einstein's field equation. So you have a very large space-time domain as well as four of them. At that point, you want to use your observations to calculate the field quantities. And if you're using a Gaussian process, the entire set of observations there, you will have at your hand a very large number of data points, and it will be very hard to actually do the Gaussian process fitting, because Gaussian processes scale as a third-order polynomial when you are trying to do this fitting, and that is very expensive. So what we want to see, even in case of very simple problems, can you use a sparse collection of data information about the Gaussian processes so that you can reduce the complexity of the problem? And that's what we do. We use a sparse variant of this algorithm that we just explained for Gaussian process-based smoothing. And this is selection of points that we will use to fit the Gaussian process is based on a very quick and greedy algorithm. So it is pretty simple actually. So we start with a random subset of the observations to begin with, and then we do a tentative fit for the Gaussian process regression with the random subset. Now, based on obtained, we are trying to include observations that are far enough from the observations already included in the selected subset to add new information to it. And this is done based on a simple kernel threshold. So you calculate the kernel value between the two different that are already in the selected subset and the new point you are trying to evaluate. And if you can see that it is far enough from all the points in the subset, then you include it in the subset, and then you reiterate over the remaining subset. And that is how, and you also make a choice that what of points that you are going to include. That is given by this value called capital N. Once you are done choosing this subset of sparse points, what you are going to do, you are going to re-optimize the kernel for the point selected, and then go in your neural network on that. So this is what it looks like. So first, we did a very did an experiment to include very few inducing points. We only took 10 of them, and as you can see here, we ended up with a very poor fit. Because 10 points on the initial time slice is hardly enough to get what is needed to recover the performance. However, when we went on to get m equals to 30, we can see that that things start to look much better actually compared to what we have for 10, and it already recovers quite a lot from the initial wiggliness of the points on the initial time space and the corresponding propagation of errors. And we found that quantitatively, the solution that we get from sparse GP smoothing is very close to the one with GP smoothing. We do lose some quality for losing some of the inducing points, but in many cases, these differences were found to be negligible, actually. So I think I'm about to conclude this presentation at this point. And in conclusion, we can say that PINNs, they have made a lot of noise in recent times, and they've been featured in many top-tier machine learning for both academia and industry. And they're very interesting and powerful tools. A lot of work is being done in this area. And one of the things that is actually the least explored aspect of it is making PINNs robust against noises in training data, and that remains an important challenge. And we extensively explored different options as regularizers, and we found that they alone cannot do an autocorrection for this error propagation that we see in PINNs. So one solution would be using smoothing, and are found to be, and their sparse variations as well are found to be pretty useful in ensuring robustness. And our experiment suggests that we can actually provide better safeguard against error propagation and also in uncertainty quantification compared to other techniques that solely rely on neural network based estimation techniques, for example, adversarial uncertainty quantification. And if you go there and you see, we also did this set of experiments for another nonlinear equation called Burger's equation, and we found that our results almost demonstratively supersede what is done by most in the literature there. So thank you very much. I would stop at this point and let the floor open for questions.
Hi. So thank you very much for the presentation. So one question I have is the Gaussian process approach appropriate for time series in general? Given that, you know, if you have something that, if you just have some time series that you don't know the generator for, is it possible that this approach might give you something that isn't compatible with optimization afterwards? I hope that makes some sense.
Yeah, I think I'm seeing what you are, where you are getting with this. I think I have in my short experience with dealing with Gaussian processes for this particular work, and in the context of some other processes as well, I have seen opinions on both sides of the aisle actually with this. I have seen some people using Gaussian process based regression techniques used for problems in other time series aspects of things, and I have also seen criticisms of it. It is not exactly I don't think there is a solid written on rock type of answer to this question. I think based on the problem that we have at hand, we expect our field to be something smooth and nicely evolving, following a very nice and well-behaved partial differential equation. And I think we found that it is a very nice way to introduce the smoothing technique. If you really think about it, we are not actually using the Gaussian process to learn the time evolution itself here, but only we are using it to smooth time, a single snapshot of the problem, and then the neural network take care of it by strictly enforcing the physics on that particularly regressed over snapshot. So in this problem, we found that is a very reliable technique to based on some other problems, this might not be the thing. I'm pretty much sure there is no one-size-fits-all answer to this.
Okay, all right, thank you.
So thank you everybody for attending this event. I hope you found it to be informative. Feel free to reach out to us if you have any questions, and we will see you next week. Thank you.